So I want to start with a very basic question that Philipp has already previewed, which is really, when we say that we don't understand quantum theory, what does that actually mean? Or to put it another way, what would it take for us to be one day able to say that we understand quantum theory? And I think that tacitly our point of reference is classical mechanics, classical physics. I think that most of us, when we're first exposed to classical mechanics, obviously that's at a pre-critical stage, but nonetheless it feels right in so many ways. It somehow coheres together in our minds. And I think when we look at classical mechanics, there has a very distinctive threefold structure. You have a classical conception of reality at the bottom, really the mechanical conception of reality. Then we have a classical mathematical framework that's really built within that overall mechanical conception. And then you have specific physical theories like classical mechanics, obviously, electromagnetism, which are built within that basic framework by making more or less specific assumptions about a domain, a phenomenon of interest. And when I talk about the mechanical conception, if you try to unpack that, you realize there's an awful lot in that mechanical conception. We have basic ideas that space and time are a canvas. So here I'm talking about the Newtonian conception. You have the idea that what exists are, say, point particles, and these point particles compose the objects around us in a simple way. There's no strong emergence. And that these particles are eternal, they're indefinitely persistent. And then they also possess properties, so that all particles possess the same basic properties. Those properties are few in number, and they're all quantifiable. And when we talk about something like motion, we assume that motion is deterministic, reversible, continuous. And then we impose additional plausible assumptions, which again have a certain sort of plausibility about them in terms of a sense of simplicity. The idea of uniformity of isolated motion, the idea that collective motion obeys conservation principles of some kind, and that if you have complex motion, that can at least be instantaneously decomposed into two particle interactions. So this makes tractable very complex motions. And then there's also a theory of observation embedded in the mechanical conception. It's presumed that ideal measurements are possible. An ideal agent can carry out measurements which are exact and non-disturbing. So you can penetrate, in principle, to the reality as it really is without disturbance. And then we have additional assumptions like there are certain perspectives that are in some sense physically equivalent, like the notion of an inertial frame. So these are the cluster of ideas, some of the cluster of ideas around the mechanical conception. And just to reiterate, I think the understandability of classical physics rests in this coherent tripartite structure above all. One thing I want to emphasize is that I don't think, as often I think it's implicitly believed, that the understandability of classical physics rests heavily on concordance with everyday lived experience. To some degree it does, for sure, but in many respects it doesn't. It goes against many of our assumptions. For example, in the process of coming up with the idea of Euclidean space, we impose a symmetry which we don't experience in everyday life between up and down, for example. If you contrast Galilean physics with Aristotelian physics, it's obvious just what a massive jump it was conceptually. The idea of past, present, and future as we experience them as being so distinct, whereas in Newtonian physics we have this basic symmetry between past and future. The idea that a living thing is somehow a special whole, perhaps a very special entity, that has no real basis in the classical mechanical framework. So there are many intuitions based on everyday experience that classical mechanical thinking certainly is not consistent with. Now, of course, with any such theory, we we understand that the idea when we're creating a physical theory is to trade some degree of immediate concordance with everyday experience in order to facilitate mathematization. And we do that using as much symmetry as possible, making things as universal as possible. We treat all objects everywhere in the same way. For example, all space, all places and all times in the same way. That all of this helps mathematizability. And of course, what we try to do is contingently recover our experience. Like, we have no problem accepting that our asymmetry up and down as we experience it in everyday life is simply a reflection of the fact that we're here on the Earth. And if we are on the float on a space station, we wouldn't experience that asymmetry. But other aspects of our lived experience cannot be recovered so obviously. And so this has also historically generated a lot of tension. Now, where we want to be, I believe, with quantum theory is we want a similar tripartite structure. This quantum conception of reality that we're looking for need not look anything like the classical conception of reality. But on the other hand, what we're looking for is this coherence. This is what we lack. So what we have today is the quantum mathematical framework. And by that, I mean at its heart, the von Neumann axioms, but there's a great deal more, and I'll come to that later. And as Philipp has already said, through some of the quotes, we treat that typically as a black box, that we know it works extremely well, and it's worked extremely well for 100 years. But we don't have the underlying quantum conception of reality. And as Philipp has explained, we've got traditional approaches to understanding quantum theory, the coining of novel concepts like complementarity, no-go theorems like Kochen-Specker and Bell, and then the kind of interpretations that Philipp mentioned, like many worlds and de Broglie-Bohm, but there are many others, Copenhagen, transactional, and so forth, which are all very important. Now, these traditional approaches have all filled out our understanding of quantum theory in very significant ways, but they're all fairly limited in obvious ways. Just to mention one example, no-go theorems focus on specific predictions of quantum theory and show that they are incompatible with a certain set of minimal assumptions about how reality is structured, but they don't really tell us how we should think about reality. So they're not that productive, that helpful in stimulating our imaginations. And Philipp has already talked about the limitation of interpretations, so I won't repeat that. So the idea then of reconstruction, in a nutshell, is, as Philipp said, we're trying to derive the formalism of quantum theory from some more primitive assumptions that we can more readily express in natural language. And the idea that reconstruction was important, that it's an important thing, was already expressed by the founders of quantum theory. Here's a quote by Pauli. He's here talking about the symmetrization postulate for handling identical particles. There's already in my original paper, I stressed the circumstance that I was unable to give a logical reason for the Pauli exclusion principle or deduce it from more general assumptions. I had always the feeling, and I still have it today, that this is a deficiency. Of course, in the beginning, I hope that the new quantum mechanics will also rigorously deduce the exclusion principle. Instead of it, there was for electrons still an exclusion, not of particular states any longer, but of whole classes of states. And I want to emphasize here that this is a very common situation when physical theories are created. In the life cycle of a physical theory, at the beginning, the raison d'etre is that it works, right? It somehow managed to integrate many regularities in the observed phenomenon of interest. And then it's proven to be very valuable because it makes new predictions that are tested. But then there's a third phase, a reflective phase, where physicists say, well, okay, often this happens decades later. This is a wonderful theory, but there are various parts of it that we don't really understand. There are mathematical features about it. There are assumptions that have been made in building up this edifice that we don't really understand. We don't grok the physical meaning behind it. And then reconstruction is a technique that's been applied repeatedly in the history of physics to understand more deeply the mathematical structure. I mentioned a conference in 2009, and I looked at it a couple of days ago, and I was just amazed by the sheer diversity. I was reminded by the sheer diversity of talks. People often point to Lucien Hardy's Reconstruction, which is obviously a very important moment in the Reconstruction program. But one of the extraordinary things about this conference is it brought together people, most of whom had not known each other, who'd labored away on reconstructions of their own for sometimes decades. So there are reconstructions going back to the 60s, 70s, 80s, long before quantum information program, but they're just not well known. They've been published and then no one has really taken them up. So I also want to emphasize, if you're interested in reconstruction as a program, there's a rich history there prior to 2000, which it's good to look at. And each of these reconstructions comes at quantum theory in a very distinctive way. I mean, that's one of the incredible things about reconstruction, the sheer plurality of approaches. So then, briefly then, the idea of reconstruction in a picture is that we're looking for a set of physical principles that we can insert, from which we can derive the quantum mathematical framework. And then interpretation, the way I see it, is really about saying, okay, let's philosophically reflect on the physical principles and see if we can be inspired and come up with a quantum conception of reality. And this two-step approach that Philipp has already mentioned, I think the first part has been emphasized a lot by physicists in the first stage of the quantum reconstruction program. But the second part is crucial. The interpretation is highly non-trivial as a second step. One of the things that's happened over the last 20 years, I would say, or the last 15 years, has been a lot more interest in other parts of the quantum formalism. So I think early on there was a lot of emphasis on the von Neumann axioms, but then subsequently there's been interest in the quantum wave equations, the spin statistics theorem, the quantum symmetrization postulate, the correspondence rules, the commutation rules, and the Dirac equation, and so on. So there's a whole cluster of bits of the quantum formalism. They're all very rich, and there's reconstructive effort going on in different areas of the world on those things. So that's an important advance since 2009. And one thing that's been driven home to me as I've engaged in step 2 over the last few years is just how hard interpretation of reconstruction really is. And also it's been driven to me how far you have to search within this great philosophical tradition to actually find resonance, to find the appropriate philosophical systems. The second thing that reconstruction allows you to do is also much more systematically and creatively explore within physics, come up with new physical frameworks, for example. So, for example, there are open questions in the application of quantum theory to questions like entanglement of identical particles. That's an open problem, believe it or not. It's not obvious how you separate entanglement and identicality. So that's an open question. So those questions are being addressed with the aid of the reconstruction program. People are exploring plausible modifications or generalizations of the quantum formalism, again, inspired by reconstruction. So Lucien Hardy has developed a framework for many years trying to embrace quantum theory and general relativity. Czeslaw Bruckner, indefinite causal structures, superposition of different causal structures. And once you reconstruct quantum theory, it's driven very powerfully home that this structure can be derived without ever really talking about the structure of space, the dimensionality, the topology, the metric of space. That really drives home the question, well, what is this thing that we call space? Is there a way that we can build that up from something more basic? So that inspires to some degree schemes for space-time, space or space-time emergence. So all of this activity has gone on over the last 15 or so years. I want to very briefly talk about the reconstructive methodology in classical physics, just to underline my point that reconstruction is not just for quantum theory. It's been used for centuries to understand physical theories that have already been created. So, for example, classical mechanics attracted great interest for different reasons. For example, Newton posited the parallelogram of forces, but his argument in the Principia is rather unconvincing, because it depends on a lot of additional ideas, like his F equals ma, force law, for example. So it requires a certain leap of faith to accept Newton's parallelogram of forces, and that weakness was noticed by a number of people. And D'Alembert, some 40 years after Newton's Principia was published, came up with a very beautiful derivation of Newton's parallelogram of forces, essentially making use of symmetries, commutativity of associativity of combination of forces, and isotropy of space. So it's a very beautiful argument that gives rise to what's known as the D'Alembert functional equation. And it gives you a completely different understanding of the parallelogram of forces. Now, you may say, well, this is a very specific thing, but the point is it's the same idea. That you've got a rule which is part of a fundamental theory. We're not really sure where it comes from. Can we see if we can rederive it from something very basic? And here we see heavy use of symmetry ideas. Similarly, Newton obviously posited momentum, but why mv? Why is mv the mathematical form of the momentum? Similarly, kinetic energy. There's a 150-year vis viva controversy. This really wasn't resolved until about 1830 or 1840, that there really were two distinct quantities of motion, momentum and energy, two conservation of principles that both had fundamental status in physics. And there are many attempts to establish a relationship between them and come up with a derivation of these mathematical forms. Same thing with Newton's second law. So these efforts went, if you look at the literature, they're there in the literature all the way up to 1900s. They were only really eclipsed with the emergence of modern physics. And to give you just one example of this, another way of thinking about reconstruction. So again, in the late 19th century, there was a lot of disquiet about the concept of force in mechanics. For various reasons I won't go into. And so Hertz was one of those who felt uncomfortable with this notion of force and tried to reconstruct classical mechanics without that concept. It's not regarded as being a successful attempt, but nonetheless you see the idea that you may want to reconstruct a formalism without using a concept that you find troubling. And of course, we've already heard about this, so very briefly, with Maxwell's equations, I think reconstruction takes on a whole different importance, because Maxwell's equations were based so much on regularities observed in the phenomenon of interest, not based on very general principles like uniformity of motion and conservation principles, which have a kind of an otherworldly aspect about them. And you might accept them for that reason alone. Electromagnetism was based on very intricate observations of phenomenon. The fact that there are two different fields, for example, is a priori not obvious at all, right? You need to look at the phenomenon to see that that's a good idea, to introduce two distinctive fields. And so then the question is, what's the deeper physical meaning of this mathematical structure? And there's a lot of mathematical structure beyond the Lorentz transformations. There's conformal symmetries, which are still not today well understood, I think, in a fundamental way, like the fundamental reason for them. But in the specific case of the Lorentz transformations, the critical point was that Maxwell's equations were interpreted relative to an ether frame, pre-1905, violating this idea of Galilean relativity. But Einstein's reconstruction then showed how you can keep relativity as long as you're willing to drop the idea of an absolute now, or say, well, it's there, but you can't access it for some unknown reason, experimentally. And the reconstruction was so compelling that it really had a profound effect on physical theorizing from that point. Ether theories were everywhere in the literature up to 1900, and after 1905 they dropped away pretty precipitously, right? So it had a huge impact on the field. And then, of course, as Philipp said, it's what directly provided the stepping stone to general relativity. And with quantum theory, we face a situation very analogous to Maxwell's equations, in the sense that the formalism was very, very strongly shaped by ideas like de Broglie's wave-particle duality, which were conditioned by experimental observations, right? So we have a formalism that's sculpted to fit phenomena of interest, not dictated by very general principles that you might accept a priori. And so the similar question here is, can we decode this formalism, see if we can get a deeper understanding of it, perhaps an impact, it may have a profound impact, just like the reconstruction of the Lorentz transformations. And John Wheeler's It from Bit, I think, captures very well this idea that so it from bit, sorry, I'll skip that. So you've all seen this quote, I imagine. So, I mean, Wheeler's idea, I think, it's very Marxian in spirit, but it goes beyond Marx in a very important way. He's expressing this idea that observation is an active process, and also that space and the continua that we posit in our theories are not fundamental. There's a discreteness to quantum outcomes, and those somehow we represent in continuous form. So we want to somehow get a deeper understanding of the continua in our theory. So a very brief remark about interpretative insights so far. Many reconstructions of the core quantum formalism make no reference to space, dimension, topology, metric, or to matter and its properties, to energy, momentum. Those are all absent. So there's a sort of a general statement I think we can make at this point that the abstract quantum formalism is not explicitly about space, matter, and energy. It seems to be about a deeper substructure to reality. And just to emphasize a fact that I'm sure is known to almost all of you, that the abstract quantum formalism is incredibly rich. I mean, the quantum algorithms and quantum computing algorithms, the quantum information protocols don't use any more than that abstract quantum formalism. So there's enormous richness in that abstract formalism. So the fact that we can reconstruct without talking about space and matter and energy and all of that is an astonishing fact, I think. Another important point, this goes back to what Philipp was talking about in terms of what insight does this give to the nature of the wave function or the quantum state. One of the extraordinary things about the reconstructions is they derive the notion of unitary evolution and the Born rule together. These co-arise. It's not like the concept of state in unitary evolution is fundamental, and we can take that as a given, and then the Born rule is a thing that we're unhappy about or want to explain. No, these co-arise in these reconstructions, so that one is not more mysterious than the other. And from this perspective, from the reconstructive point of view, quantum states are introduced simply as an operational means to connect measurement outcomes. So we consider a series of measurements and interactions, and quantum states are simply a mathematical object that's introduced in order to connect measurement outcomes with each other. Now, I just want to briefly talk about identical particles in quantum theory. That's something I've been working a lot at recently, and I think it may be a good example to show how reconstruction can connect to interpretation and to philosophy, to metaphysics in particular. So we're now talking about the atomistic conception of classical mechanics, was focusing on that particular idea that the physical world contains or consists of point particles that persist over time, possess various properties, static and dynamic properties, and can be precisely measured without causing disturbance. And this is a well-known fact, particularly in philosophy of physics literature, that there's a long debate, which has been going on for decades, as to what is the nature of identical quantum particles. So are they persistent? Are they re-identifiable? And if not, how should we conceptualize them? Right? We talk about electrons, we assign them mass and charge and spin. We speak of them as if they are particles, very much like the particles of classical physics. Of course, we hedge that and say, well, we know that they're not really continuously localized, okay, but we still talk about them as persistent entities. But is that really accurate, right? Is that really fair? And what we have to go on is a very specific part of the quantum formalism, the symmetrization postulate introduced by Dirac and Heisenberg independently. And this briefly says that if you've got, say, a helium atom and you want to solve for the wave function of that, then what you have to do is work out the state, work out a state, for example, a product state of 1s and 2s or something like that. And then you have to also consider psi here, x2, x1. In other words, you don't just consider each one of them separately. And Dirac's rationale was that you have a formal redundancy in the theory if you just allow each of these states separately. So he proposed to break that, remove that redundancy by disallowing each of these states separately and saying that you're only allowed to use a symmetrized or an anti-symmetrized version of that state. And this recipe remarkably recovered what was then known about quantum statistics. It reproduced the arguments of the results of the Bose-Einstein and Fermi statistics. So this is what we have to go on. Dirac also proposed an interpretation at that time. He said that particles in a system are absolutely indistinguishable from each other. And this interpretation has become so closely tied to his formal recipe that it's repeated in virtually all the textbooks on quantum theory, much of the literature in physics, and it's repeated in most of the philosophy of physics literature as if it's part of the formalism. But Dirac's interpretation is an interpretation. It's something added on top of this recipe. And I want to emphasize that there's very good reasons for saying that this doesn't really make sense if you think about it carefully. The first is that when interpreting primary experimental data, persistence and re-identifiability are routinely assumed, right? So if you look at a bubble chamber image like this, what an experimental physicist says, well, these are particle tracks. But of course, it takes us to say that this sequence of bubbles are generated by the same particle. So the experimenter is assuming that. And you might say, well, I mean, a philosopher of physics might say, well, you know, we could just sort of bracket that. We needn't take that seriously. But a particle physicist would balk at that because it's the geometry of these tracks which enables us to learn about the micro world. For example, to actually measure the properties, the intrinsic properties of these subatomic particles. So we have to take these assumptions, which are implicit in experimental practice, very, very seriously. Another issue is that this idea of indistinguishability, if you mathematically formalize it as the so-called permutation variance condition, it doesn't yield a mathematical form of the symmetrization postulate. So there's a big gap between Dirac's idea of indistinguishability and the mathematical recipe that we know actually works. And so the idea then to make progress is, as we've said many times now already, is to first of all reconstruct or derive the quantum symmetrization algorithm and then interpret. And one of the very important points about this approach is it avoids implicit interpretational assumptions. So in almost all the philosophy of physics literature and most of the physics literature, it's assumed that the indices 1 and 2 in psi x1, x2 refer to particle 1 and particle 2. That's a very strong metaphysical reading that it's so natural for us to to follow because it's familiar from classical thinking and it's embedded in our language. We keep on talking about two electrons, electron 1 and electron 2, but that's a very strong reading already. And it turns out, from my perspective, that's a mistake, and that only comes to light through reconstruction. So let me briefly show the basic idea here. So I'm taking quantum mechanics in the operational sense, that we have a physical system that persists from beginning through end. We have measurements, we have interactions. The critical thing, as Wheeler mentioned, to take away from quantum theory is that measurement is an active process. It's not a passive registration of what already is there. From a point of view of experimental design, what that means critically is that you must design experiments to keep interactions and measurements apart, right? Because measurement is an active process. So the point is that in classical physics, you can imagine taking an electron and putting it in a magnetic field and tracking it as precise as you wish at the same time, no problem. Quantum mechanically, you can't do an experiment like that. You've ruined the experiment if you try to simultaneously track the electron arbitrarily precisely. So for example, if you have a simple electron diffraction experiment, a physicist would say, well, electrons are emitted from the cathode and accelerated, deflected, and hit the fluorescent screen. But in fact, there's no tracking, there's no precise tracking going on from cathode to screen. The inference that it's the same electron that strikes the screen as was emitted earlier from the cathode is an inference, an indirect inference. So let's talk about how this affects something like re-identification. Imagine we've got a muon and an electron, and we measure their intrinsic properties initially, and then they interact in some way, and then we want to re-identify them later. We can certainly do that simply by measuring their intrinsic properties later on. But if you've got two identical particles, because of this issue of having to keep interaction and measurement apart, it's not possible in general to re-identify, except in certain limiting special cases, which are very important. But in general, you can't do this. So now we really face a fundamental question, which is really a philosophical or metaphysical question, which is really if re-identification is sometimes not possible, which is in this arena of interaction, is the assumption of persistence still justified? So we've got, let's say, two electrons coming in, leaving tracks, right? They leave tracks before, they interact, and afterwards there are tracks. So we could say that there are two persistent entities before and after, but are we really justified in our mind's eye of thinking of the arena of interaction containing two persistent electrons? I would say that there we're extrapolating beyond what we have experimental access to, right? So if we're being ontologically modest, we might say, well, we should question that assumption. And the question then is, how do we proceed? How do we proceed without that assumption? And so this now gets to how you reconstruct the symmetrization postulate. The idea is to go back to the data, go back to the operational framework, right? So we've got here two flashes and two flashes later on. And the usual story we tell, which is that there are two persistent entities all the time which exist, and either this happened unseen in between, or this happened. But if we're being modest, we realize, well, there's another possibility, that there's a single persistent entity which generated those two flashes and those two flashes. And in this way of thinking, we're regarding the two outcomes, the two flashes, as a single outcome performed on this holistic system. Now, this obviously goes far beyond anything in everyday life. We normally assume that objects exist in space just where they appear. But here we're saying, well, there's another possibility, logically speaking, which is also consistent with what we experience in the lab. So you may say, well, we've got two models. How do we make use of them predictively? It turns out that you can do the following. Within the Feynman framework, which is very well suited for these models, you can describe each of these models, each of these transitions. So the direct transition and the indirect transition you can describe in the persistence model, and likewise the non-persistence model. And here I inject the physical postulate. Now this is something that makes sense in this context from an almost mathematical point of view of creating a kind of closure, is to say that this alpha in the non-persistence model is a function of the transition amplitudes of the persistence model. And then there's an analogous assumption for what happens if you've got flash, flash, flash. Similar idea that the transition amplitude in the non-persistence model is a function of the corresponding transitions in the persistence model. And then it turns out, remarkably, you can derive what H is. I won't go into the details, but just to give you a very quick idea of what this looks like, you can calculate certain amplitudes in two different ways. And by requiring consistency, you get a functional equation. So here we can work out the amplitude for the bottom part of this experiment, and then for the top part. And then we can use the Feynman product rule to multiply those amplitudes together. But alternatively, we can consider that as a block and then work out the amplitudes of those four contributing pieces, again using the Feynman product rule. And then we can combine those all together using this g function that I introduced. And so we end up with a functional equation, which has got to be true for all sets of parameters within a certain range. And so when you solve the functional equations, and there are four of them in total, you get the Feynman form of the symmetrization postulate, fermions and bosons, plus or minus sign. And you end up being able to generalize this rather straightforwardly to any number of particles. And for those who are familiar with this, the interesting thing about this derivation is that there are no paraparticles. There's nothing else other than the fermions and bosons. So it's empirically spot on, right? Corresponds to what we find necessary to use in practice. And when you convert all of this to the state language, you find something very interesting, that on the right-hand side you have the states in the persistence model, where x1 and x2 refer to particles 1 and 2. But on the left-hand side, the state is defined in reduced configuration space, so-called, where x1 is the leftmost flash, x2 is the rightmost flash. So the meaning of x1 and x2 differs with respect to the model in which the state exists. And you can then turn this into what looks like the symmetrization postulate, but now the meaning of x1 and x2 is muddled, right? So the proper place to look, the proper setting in which to look at this is the previous equation. So now comes the interpretation. And so I did the reconstruction in 2015, and then it's taken many years to sort of gradually peel away the layers of understanding about what it actually means. So first of all, the symmetrization postulate, it's not a selection rule. It's got nothing to do with permutation and variance. It's really a bridging rule that connects together two different models of particle-like events. And one of the interesting things about this is the long-standing issue, is how does symmetrization tally with the idea of separate systems? So physicists use a meta rule to decide when to apply the symmetrization postulate and when to suspend it. In this reconstruction, that's automatic. The idea of separate systems is built into the reconstruction. So interpretation, the first idea is that these are really incompatible models, different models, object models of the same data. They're incompatible if taken seriously, and yet they can be mathematically synthesized to give rise to the symmetrization postulate. So I would argue that these are actually complementary models, strictly in the sense of Bohr. So there's a new kind of complementarity hidden in our treatment of identical particles. And then briefly, some of the metaphysical implications. There's a long-standing debate in metaphysics about whether objects, persistent objects or events are primary, which is ontologically primary. This has been discussed by Russell, Whitehead, C.D. Broad, Quine, and other people. Also more recently in the quantum foundations literature. What comes out of this approach here for identical particles is that events have priority over objects in the microscopic realm. Why? Because you can't, if you look at a microscopic event, you cannot uniquely identify the object, the microscopic object that's responsible for that event. But there's a caveat, which is that the operational framework presumes a persistent frame of macroscopic objects. So there's a kind of hybrid structure here. Going back to Hume's skepticism, famous skepticism about persistent objects, that raises an important question philosophically, is when is it reasonable to doubt the persistence of objects in the world? And I would say that what we can see here is that it's when persistence loses empirical cover. That is, on the basis of other assumptions that we hold dear or principles that we hold dear, it's not possible in principle to re-identify. That's when we should doubt persistence. And this follows a common pattern in the history of development of physics, where an assumption like absolute rest or simultaneity of distant events or the idea of rotation with respect to absolute space were taken as given for a very long time, but eventually recognized to be not empirically accessible, and then were in some way relativized. So I'm proposing that we have to relativize the idea of a persistent object in the case of a system of identical particles. So finally, just a remark about the idea of parts, wholes, and emergence, again, another very big topic in metaphysics. So from the atomistic point of view, we're saying, look, what exists are the atoms. The wholes are merely rearrangements of parts. And as I alluded to earlier, that creates great difficulties in making sense of living things or higher order things in the world. What's coming out of this interpretation and reconstruction is that when we're talking about identical particles, we have to use two different object models to capture what's really going on. The persistence model expresses the idea of parts, that there are parts always existing. The non-persistence model captures the whole. And it's really the synthesis of these which is adequate empirically. And the synthesis also shows a theoretical role played by the whole. And so what we have here is actually a case of strong emergence right here in quantum theory. So we could talk about a helium atom containing two electrons, potentially, not actually, right? So they're potential because the non-persistence model is needed to describe them. When they're widely separated, the electrons can be regarded as actually there. Conversely, when the atom is recreated, we can say that holistic object emerges. So I'll leave you with some references. The first one is actually a link to the videos of the 2009 conference. They were all recorded at Perimeter Institute, so you can actually watch those talks at your leisure. The other three papers here are about reconstruction, about the reconstruction program. And these articles here are more specifically about identical particles. The first is the reconstruction itself. The second and third are my gradual attempts to interpret the reconstruction. Thanks very much for your attention. Okay, so it's when you press it, it goes mute. That's live. Okay, so
questions.
Thank you for your talk. I'm really wondering why you are cutting out space, matter, and energy in your reconstruction program. It seems to me astonishing because you are also referring to Husserl and phenomenology, and Husserl speaks about models. Wheeler speaks about pre-geometry. Do you think something like fundamental higher dimensional geometry would be helpful?
Yeah, thanks for the question. the idea of reconstruction isn't to deliberately cut out space, right? To say, well, we deliberately want to keep it out. It's more like saying, in the process of reconstruction, what's the absolute minimum we need to derive the von Neumann axioms for finite dimensions? Or, like I've said here, reconstructing the rules for identical particles. Again, you don't really need to talk. I know I've described everything in space, but space isn't actually needed. Certainly not the metric or topology. Well, maybe topology, but not the dimensional metric of space. None of that is needed. But you're right. I mean, in the end, we then, once we've got that understanding of quantum theory, we want to indeed consider ways of recovering space or connecting to our space-based intuitions. I mean, so, for example, Penrose has this beautiful work on spin networks, and there are many modern sort of variations of that as well. So that indeed, but you might say by reconstructing quantum theory without reference to space, it makes it all the more imperative to say, well, how on earth does this mathematical structure, which is so rich, how does it interface with things like Euclidean or Riemannian geometry? And what is that connection?
Okay, thank you for your very instructive and enjoyable talk. I have a question which actually follows up very nicely regarding your question, because I think effectively you must have made use of the three-dimensional space in your derivation of the symmetrization rule or postulate, because if you limit yourself to two spatial dimensions, you don't get only fermions and bosons, but you can get anyons. And so I think this interplay between the space and the dimensionality of space and your arguments can be probably made very nicely explicitly in an explicit form by looking at anyons and see where does this assumption goes into your argument.
Yeah, thanks very much for that. Yeah, I mean, I've been intrigued by the topological derivation of the symmetrization postulate, something I looked at a number of years ago in a lot of detail. We're getting a little technical here, but my current understanding of it is that derivation is really not about identical particles. It's about what happens topologically when you are in two dimensions and you assume that particles can't coincide. So in other words, I also have doubts about the consistency of the Laidlaw and DeWitt argument, the one that's most rigorous. So my belief currently, and it's not absolutely ironclad, is that the symmetrization postulate doesn't rest on dimensionality of space at all. But when you have electrons or whatever it is confined to two dimensions, then overlaid on the bosonic and fermionic behavior, whichever is applicable, because of the nature of the particles themselves, there's also topological behavior overlaid on top of that. But I'd love to discuss that with you. It'd be very interesting.
Thanks for your talk. I very much enjoyed it. This relates to the previous two questions, might even be the same point maybe. So you mentioned that the reconstruction program doesn't need to make reference to space, time, matter, energy. I'm also doubting how this works. I mean, it starts even much earlier than just the three-dimension necessary to distinguish bosons from fermions. Which is, if you talk about a measurement outcome, right? You have to tell me, where does it live?
Right.
And what does it mean? How does it relate to the physical world? So unless you think that the reconstruction program is not a full theory or just part of a theory, I think you need to also include statements like that in the reconstruction program to have a full theory.
Yeah, I should just to clarify, the reconstructions all make use of time. So the ordering of measurement outcomes in time is critical. Interestingly, they do rest on time order, but they don't necessarily make use of a metric in time, so there's no need for a metric over time. They also need the concept, at least mine does, and I believe they all should actually, the idea of immediately afterwards, because we need repeatable measurements. So time comes in. You're right that some notion of separation exists. Right, we need to be able to analyze the world into system, measurement device, interaction. There's some sort of analysis going on, but it's certainly, to me, much more much less, we have to assume much less than assuming the full structure of space, which I understand to be topological, dimensional, metrical. Most of that information is never coming in. And if you said space is 5-dimensional, the reconstruction would work just fine. If you said that the metric of space was different, it would work just fine. So we need just enough of the idea of that we can analyze the world into different parts, right? And that's enough. That's what I guess I'm getting at. That if you look at the reconstructions, that they don't ever really say what the dimension of space is, what the topology is, what the metric is. Is it hidden in some way, or is there something which you might regard as related to space? Yes, but it's certainly much less than space itself, I think.
I just wanted to make a quick comment on that because, I fully agree with you. I mean, the reconstructions are really about, a framework of operating in a lab. Of course, ultimately, we have in mind that this is done in some kind of space, but the theory doesn't make any reference to that, and it also doesn't need to. And so the quantum formalism in principle could, of course, also work in other geometries. How it would then relate to that geometry is a different question. But it's a bit unfortunate that Markus Müller isn't here today because his talk is exactly about this. I think he's coming on Thursday, so it's really about going beyond just looking at the pure quantum formalism, but also asking how it fits into some kind of space-time environment at a very basic level, and then you can see, for instance, if you want to kind of operationally make sense of some of the things you do in quantum theory, some of the operations you do in the context of space-time geometry, that of course puts very stringent constraints on what kind of space-time structure is actually consistent with that. But that's something that goes beyond the pure quantum formalism and deriving just the formalism at face value. I think in Markus Müller's talk we'll hear much more about that.
Okay, perfect. We have one more question.
Okay, thank you for a beautiful talk. So basically I want to also ask a question to this discussion. Probably we will discuss this sometime later or in the talk of Markus Müller. And a lot of things I wanted to ask are already addressed, but one thing I was wondering now, besides all the issues with causality and stuff, is actually the particle interpretation itself. Because as far as, at least as I know from my master studies, you need Lorentz symmetry to talk about the notion of a particle on a fundamental level. And if you, for example, quantize a scalar field in a specific curved spacetime, you cannot actually introduce the notion of a particle because the whole formalism fails. So I really wonder how this all works. Talking about particles if you don't talk about spacetime. I see that you maybe don't need a metric or something, or at least a notion of closure in form of a topology or something. So this is really something that would be interesting.
Yeah, I mean, it's an incredibly rich topic, identical particles, right? So what I'm deliberately doing here is talking about the context of fixed particle number. And again, I'm using the word particle because it's familiar, but we could just be talking about abstract subsystems. The derivation goes through, if we just talk about abstract subsystems, that's enough. So these things don't need to be in space. As long as we can conceptually analyze the world and say we've got this subsystem and that subsystem, we're good. The derivation goes through. The question of then how that links in with quantum field theory, which I think is really that question, that brings in a whole load of other issues. So what typically happens is we take the symmetrization postulate in non-relativistic quantum mechanics, meaning fixed particle number, and we go over to Fock space, we transport the symmetrization postulate into the commutation and anti-commutation rules, and we get something of a leg up when it comes to the Hamiltonian for the system. And then we allow superposition of different particle numbers, modulo certain constraints, some certain not selection, super selection rules. And then we have a formalism. And then we impose yet more structure on that, like Lorentz symmetries. So there's an awful lot of moving parts when we get to quantum field theory. And I don't feel qualified to talk about what happens in that context. That's another big area of like, well, okay, the ideas I've described here, when you take them across to QFT, what happens, what changes? But these are great questions. Those are great questions.
Yeah, because I feel like this issue of persistency is kind of addressed by making the field the fundamental quantity instead of the particles.
Yeah, so maybe we discuss. We have one final question.
Thank you.
Please, very short. We're fine. Okay, perfect. So then it's time for break. Thanks again.